All right, so thanks everyone for tuning in. Welcome to the JG Lunchtime Learning Series, the WebGL edition. So there are a lot of important concepts with WebGL that I'm trying to pack into a short amount of time. So if I get too far ahead or I kind of gloss over something quickly, just let me know. Don't be afraid. And there'll definitely be time for questions after too. I accidentally muted myself. Okay, so what is WebGL? Keep muting myself. All right, so WebGL is a JavaScript API that utilizes your computer's GPU to render graphics in a web browser. And the GPU is very important because it really is just a super efficient number crunching machine. And in order to render a 3D scene, there's a lot of math that needs to happen, and the GPU is designed to do that. And it's based on OpenGL, which for a while has been a widely used standard for non-web browser graphics. It's used in things like game engines, it's used for video games, graphics, simulations, and much more. So why use WebGL? Use it to enhance your website, creating like an interactive 3D experience within your web browser. Gives you direct access to the GPU, as just mentioned, which can really optimize graphics performance. You can see from these examples, there's like a living room simulator. You can move around couch cushions. There's interactive experiences. You can rotate 3D objects. And a lot you can do. So kind of touch a little, but I'm going to get back to it. Why use the GPU? So it's got parallel processing, memory parallelism, and high-speed memory. And so these three things together just allow it to do a lot of mathematical operations very fast. So we're going to start with something called the render pipeline. And so for WebGL, this is basically how it works. You set up things. The green is going to be the setup. So we have to take information about what we want to render and put it onto the GPU, because the GPU and the CPU are two different things. You have to be able to, they don't share memory, so you have to be able to take memory from the CPU, get it on the GPU. So the green section is going to be what helps set that up. The blue is actually what is going to happen on the GPU and what we have control over. Some of it we don't have control over, but the shaders we do. I'll get to what a shader actually is later. And then the red is the actual front end part. So the HTML, which it's actually an HTML5 canvas. So first, before I jump into that green section, I'm going to briefly explain what something called a model is and why it's so important. So models are just objects that are made up of primitive shapes. And what's a primitive shape? It's really just a triangle. Sometimes they're quads, but we're just going to think of them as triangles for now. And so primitive shapes are made up of things called vertices. And if you look at any of these images, you'll see that each of these models have the points on them. And each of those little points that are connected by lines are called each one is called a vertex. And each vertex on a model has data that's associated with it. And this data is called vertex attributes. And a vertex attribute is simply something like a position. So each model with respect to some origin, or each vertex with respect to some origin has a position. And that's one example of a vertex attribute, but I'll get back to that later. Hopefully that made sense. So now we're going to start in this green section, the setup before the GPU. So this is, like I've been saying, the part of the pipeline that takes vertex data from the model and it prepares it for the GPU. So I'm going to go over some things individually. I'm going to go over vertex data, which we've mentioned, something called a buffer, which people might be familiar with something called a buffer already, but I'm just going to explain it here as a big clump of data that we give to the GPU. We kind of pack it with our vertex data, and then the GPU is able to use things in the buffers. The memory from a buffer actually gets copied onto GPU, if you're really curious. And then matrices, I'm not going to go crazy in depth on the math of this because this is not a linear algebra LTL, but the gist of matrices is that they're used on the GPU and they calculate where a model as an entirety is positioned in the space. So it controls, I'll get more into it later, but it's something called matrix transformations if you're really curious, but I'm not going to go into it. Okay, so vertex data. Vertex data is made up of vertex attributes, which we talked about earlier. And so position is one example of a vertex attribute. If you look at this picture on the right, there's a cube model I have, and you can see all the points are the vertices. And with respect to that origin in the bottom left, you can see those two, the top left and the top middle vertex, have those positions. And that's a position attribute of those two vertexes. And then they all position, or another attribute is something called a normal. And basically, it's like any physics. If you took a physics class, it's the perpendicular direction off of a surface. So each vertex has a normal. And this is very useful for light calculations, which we'll get to later on the shader. An example would just be like the up direction 0, 1, 0. And then another attribute would be something called a texture, which is slightly more complicated, but you can map a 2D coordinate from a 2D texture image onto a vertex. So when a texture is being applied to the object on the GPU, you can actually interpolate pixels that aren't a vertex using the texture map. So it can, if you had, if you can see my mouse, if you had this red arrow vertex assigned to a vertex, and you had this other one right here to the left, the GPU can actually interpolate all the colors in between them. You don't need to specify specifically. So texture mapping is very useful. Okay, so something I haven't touched on yet or mentioned is something called a vertex indice. And so each vertex, when you get it from a model, has an index. So if you look on the right, you got index 0, 1, 2, and 3. Those are just the place in the list of vertexes. And so a model that I mentioned has a list of these indices. And the indices can tell the GPU how to actually group vertexes into a primitive shape, which is a triangle, like I mentioned earlier. And if you look at the indices list, which is right below, you have 0, 1, and 2, which so 0, 1, and 2 can make a triangle, and then 2, 3, 0. So each 3 consecutive indices will make a triangle. And this is actually very important because it saves memory. You don't need to store redundant vertices. So if I didn't have an index array, I would have to duplicate the 0 index and the 2 index. So it's not as important now saving memory, but it used to, back in the old days, was very important to save memory on GPUs. And that's what I already mentioned. So next we're going to get to buffers and what uniforms are. And uniforms are very closely related to matrices. So they're both really just ways to get data from our program on the CPU to the GPU. And so a buffer, which we've already explained a little bit, is just a clump of memory that we give to the GPU, and it stores information about vertex attributes. And then indices, which I just mentioned, actually have their own separate buffer, which is called an index buffer. Not super important to know, though, for this. And then a uniform variable. What is a uniform variable? It's a variable that we can give to the GPU, and then it remains consistent across the entire shader pipeline. And what's the shader pipeline? It's that entire blue section. So every step of that blue section has access to a uniform variable. Actually, I'll go back. So an example of a uniform variable would be our matrix. And so each step in that shader pipeline can use a matrix. And so I'll actually talk about that now. So how do we actually represent an object in 3D space? We can do it by using something called a transform, which is 3 vectors: position, rotation, and scale, which allows us to give an object an XYZ spot in space. It allows us to orient it, which is a rotation, and it allows us to dilate it. So if the scale was multiplied by 2, the object would be 2 times bigger. Scale is not super important usually. And so these 3 vectors can be taken and packed into a matrix called a model matrix. And that's where the matrix transformation comes in. But all you really need to know is you can take those 3 vectors, pack them into a model matrix. And so the GPU, through a uniform variable that you pass in, is able to take the model matrix and go through every single vertex position, and it can calculate the final 3D world position of the vertex. I know that's a lot probably that I just said there, but here's a very simple example. So if you look at the picture in the top right, you have 2 different cubes. And so um, they're both the exact same model. They have the same exact vertex data. But why are they in 2 different spots? Because they have a different model matrix. So this calculation that happened for every vertex, on one shader pipeline, it was this left cubes matrix, and on the other it was this, and that happened for every vertex. And that's how you can move objects around the world. So matrices and uniforms are very important. So that's kind of how we get information onto the GPU. I hope that makes sense. That was still kind of a high level, but now we're going to move on to the actual shader pipeline itself, which is all on the GPU. And so the ultimate goal of the shader pipeline itself is to render a 3D scene, determine what all the pixels will end up on your 2D screen. So it's going to render a scene in 3D and then translate that into a 2D image of pixels. It's really just that. And it's going to go through each of these steps: vertex shader, what primitive assembly is, rasterization, fragment shader. I know that it sounds complex, but they're actually pretty simple, and I'm going to go through each step individually. So I know I've been talking about shaders. It's a super big buzzword in computer graphics. You might have heard of it, might have not. If you played something like Minecraft or seen a game say it's compiling shaders, that is where you might have heard it. But it's really just a customizable program we create. It runs on the GPU, and it just controls how an object is rendered. And there are a few types that all serve different purposes. The 2 main we're going to focus on are the vertex shader and the fragment shader. But there's also a few other types that I'm not really going to get to the weeds of, called the geometry and tessellation shader. If people have questions after, I can go over it, but we're really going to focus on the vertex and the fragment shader. So now we're back onto this pipeline of the vertex shader. I'm going to go through each step. So the vertex shader, its main purpose is for usually coordinate transformation. You really can do anything you want with it, but for a basic program, it's just going to be taking a vertex and it runs. So a vertex shader runs on each individual vertex on the G. That was horrible wording. It's a compiled program that runs on each individual vertex, and it runs on the GPU. So we gave the GPU our vertex buffer, and it has all the vertex positions. And the vertex shader gets every single one of those vertexes and runs for each one. And the GPU is so cool because it can actually optimize this process, and it can parallelize that and run every single vertex at the same time, which is really cool. It could take all that entire vertex and just output it all at once. And so it gets access to all the vertex attributes, like I mentioned, like position, normal, and texture. And it also gets the uniforms too. So it gets the matrices. And so that calculation I said where it just multiplies the matrix by the position, it just does that, and then it outputs a final world position. That's basically all the vertex shader does. Hope that makes sense. Oh yeah, and vertex variables can be outputted from the vertex shader that can be used later on in other shaders like the fragment shader. So now we're going to move on to primitive assembly and rasterization. These we actually don't have control over really. They just happen, but it's important to know what they actually do. So primitive assembly is kind of exactly what it sounds like. After the vertex shader, it's just the creation of those primitive shapes from the calculated vertex positions. And we had that index array that I mentioned earlier. So the GPU knows how to make those primitives. And then we get on to, that's really all primitive assembly is, very simple. Then we get on to rasterization, just slightly more complicated, but at a very high level, it just takes 3D geometry that's outputted from the primitive assembly and it converts things into 2D fragments on the screen. So what's a fragment? It's really just, it's basically a pixel, but they're potential pixels that store information that get passed to the fragment shader. And so an example of a fragment would be, it really is just a pixel, but it goes through every single, let me think of a good way to word this. So yeah, if you look at this triangle, it basically can break up this continuous surface that's not in computer language, and it breaks it into a triangle that is in computer language of pixels. And each of these pixels is given to the next step of the pipeline. Hope that made sense. And a really cool part about all this is the outputted variables from the vertex shader during rasterization get interpolated. So say each of the 3 vertexes, the points of the triangle, all had 3 different normal values, and you wanted to output a normal value of a fragment to the fragment shader. If you had the very center pixel, it would actually just basically be the average of all those outputted. So you don't have to worry about doing any of that yourself. It just happens for you. Yeah, and that's what I just mentioned. Sorry, that was a poor way of explaining it. So now we're going to move on to the fragment shader, which is what I've been talking about. So really, it has one purpose, and it just gives color to those rasterized fragments. And it's basically the final step of the pipeline. There's a few things that happen after, like something called depth testing, anti-aliasing, a lot of things we might not necessarily control. So it's typically the final step. And it's just like a vertex shader, it's a compiled program that runs for each individual fragment on the GPU. This can also be parallelized, which is why it's so efficient. And it can use those variables exported from the vertex shader in the uniforms that I had also mentioned, and it always outputs a single color. So if you look at, I don't know if you can even read this, but this very simple fragment shader, I pass in a color as a uniform, and all it does is output a color that is the uniform. So every pixel in that, it's not replicating this image, but every single pixel outputted by this code would output whatever color is the uniform color. That's like the most simple you can get with a fragment shader. So hopefully people are still following along, but I'll kind of just try to solidify things a little bit more with a summary. So this is a nice, easy to understand diagram. So we had our vertex buffer objects that we set up with attributes and uniforms, and those all get passed into the shader pipeline. And then you have the output variables that can go in between the vertex and fragment shader. And then all of that goes out to the frame buffer, which is just an array of pixels that we can render on any 2D screen. So now, talked a lot about computer graphics, but where does WebGL fit into all this? So we're going to get to that. So there's this thing called, that everyone here now probably knows of, is an HTML5 canvas. And so the canvas actually just takes the frame buffer that's outputted from the GPU and renders that. It's that simple. It does it all for you. And in order to actually set these things up, HTML5 Canvas has something called a WebGL rendering context attached to it. And basically all modern web browsers support this. So you could just, there's a function I'll show you later called get context, and you can get a WebGL context, and every canvas has this. You don't need to import any libraries. Any web browser just has the ability to call this API. And so the context is just the JavaScript API that allows us to create things like buffer objects that we mentioned earlier. It can tell the GPU how to use the buffer data, compile shaders, create shader programs, set specific render settings, and a lot more. And don't be overwhelmed by this. I'm just showing if people want to see examples of code. I'm not going to go through each individually, but this is an example of how you'd use it. You just get the context, and then there's all these types of functions you can use. Okay, so how are we going to integrate it with an actual web application? So people might know about this. It's called request animation frame. So it's a JavaScript function that's built into web browsers, and you can pass in a callback function to it that returns before the next browser repaint. And typically, it runs at 60 frames per second, which is most of our computers, but it usually actually just matches your display refresh rate. And if you want to just keep re-rendering it every frame, you can just call request animation frame within your callback function itself. So it's not quite recursion because it's a callback function, which is cool. So it's not going to do anything crazy. And say you don't want to render every single frame, it has a timestamp value. So you could actually limit how many frames per second it's rendering, or you could say you're using something like React, you could have a Boolean state variable. So you only want to render the scene when something happens, and that would also save a lot of your GPU. So here you can also do things using browser events. So say you want to use HTML DOM events to interact with your scene. You could do something like when a mouse is clicked, you rotate the object. And rotating the object is usually just editing that matrix uniform variable, like I was saying. And then the vertex shader would then take that new matrix and adjust all the vertices accordingly by rotating them. And if it's doing this on every mouse down event, you'll just get a continuous rotation. And the coolest part of all of this is that if you were using something like OpenGL, which is the non-web version of this, there's a lot of setup with input libraries and window libraries that you'd have to actually take the frame buffer and render it in some window. Because we're using a web browser, all of that out of the box because you have listener events and you have the canvas. And so the last thing I'm going to talk about is something called Three.js, which I bet a lot of people have heard about. So it's a library that abstracts a lot more of the complicated WebGL concepts that are easy to learn, and it's very easy to learn. And you still have direct access to shaders because it's just abstracted over it. And it's a very quick and easy way to implement 3D web graphics quickly. So say you had a client that wanted you to make a web app really quick, or make a 3D web app or 3D web demo really quick. Three.js would probably be the way to go because it does a lot for you out of the box. But if you really wanted to understand WebGL and 3D graphics, it's definitely worthwhile to create your own simple graphics engine first. But Three.js can give you a lot of things out of the box, like shadows, shaders, a lot of lighting, materials, scene management, animation, the models, raycasting, which is actually being able to click things within a scene and take a 2D screen coordinate, shoot off a beam into your 3D scene and calculate what object it hits. That's very complex math, which is all possible with WebGL, but you just have to do the math, which I think is cool, but not everyone wants to do that. And if you're really curious of what a WebGL project looks like, I did make a little demo project that reinforces some of what I'm talking about, hopefully. So I can send the link in the chat here, or if you don't get it, just DM me. But yeah, hopefully you learned something. Raise their hand. If anybody has questions, just speak
We
out.
had Lucas and Ryan, perhaps. I don't know if they actually were raising their hand or just accidentally click that.
Yeah, I was very excited to clap my hands. I clicked the wrong hand.
That'll happen.
Yep, Isaiah.
Are there, I guess, built-in mechanisms to be aware of the user's hardware? Because I can imagine if you're getting really crazy with what you're rendering, someone's computer might heat up.
I'm sure there is. I actually have not dealt with that too much personally, but I would assume there is, or there's other libraries you would import to actually detect that. If anybody else knows of ways, also feel free to answer, but that is a good point. Zach.
Oh yeah, I was just wondering, what's the kind of the best practice? Are there libraries or documentation that will help you if you want to integrate this into React? Particularly, I'm thinking about like how you do like state management with a WebGL component.
Yeah, so for React specifically, that's actually what my demo project is in. So you can what I'm talking about now, you can also go look at, but it's usually good to use a reference. So you actually make your WebGL program as I use TypeScript, so a bunch of TypeScript files that are separate from your actual React application, and then you just use a reference to that, and then and your reference would just be a class called like render or something, render scene. And so within that class, you would have like a start function that would set up your scene, render it, and then no matter how your component refreshes, it still keeps it constant.
Very cool. Thanks.
What's some major pain point you've noticed, or if any pain points you've noticed working with WebGL? And like, how have you tried to accommodate that?
Okay, so I've actually talking to Ryan Chandler about this a little bit. So when you do not get a lot of good feedback with shader programming, because shaders, usually when you give them, maybe there's programs that will give IDEs for them, but they're really just strings, and you use the WebGL context to compile them, and you can get compilers. But once it's compiled, if there's something that's not working or you didn't link something properly, it doesn't tell you, it just won't render anything. So you have to be really careful about like exact matching strings and things like that. Otherwise, it just won't even tell you that it's not rendering or why it's not rendering. It just won't render, which is funny. You'll go from nothing rendering to fixing one line of code and then everything renders. It's crazy.
Any other questions? Looks like that might be it.
Actually, I have a question. Not to spam down with questions, but well, what do you think like the limit of using WebGL is? Right, like what kind of product or application like would you use for WebGL versus like going with something like a gaming engine like Unity, going away from the web? I don't know if that's a great question, but hopefully you get what I mean. Because we encountered this on Logic where we were like, do we need WebGL for this, or should we just build an entirely separate application for rendering some of this 3D stuff? And we landed on WebGL, but I was curious what you think the limit is.
So my guess would be, because it's in a web browser, and the web browser is what calls your own computer's GPU. If you're not using something like server-side rendering, you would actually, it would be hard to guess what everybody's hardware is. So and you can't you would have to test along all the different types of hardware to make sure it runs smooth. So someone with a really bad computer might not be able to even run your app, and you'd have to be aware of that. So you would either have to optimize a lot or maybe do server-side rendering, where it's just, because it's JavaScript 2, I'm assuming it's probably not as quick as something like OpenGL, which you're usually writing in like C, C++, which is compiled. But that's also just a guess. But yeah, the main answer to that is, I think, just people using your web app with different types of hardware. It might be hard to account for all the different types. Like really bad, really good probably wouldn't matter, but I hope that makes sense. Brennan?
Yeah, so just kind of tailing off of that one, I know that the way that we get around that in doing regular animations in the browser is by using that request animation frame, right? And then it'll actually kind of like tailor itself to how quickly or how slowly the user's computer and browser are able to actually render. So it's like kind of 30 or kind of 60 frames per second or something like that. Do you know if there's something like that that's kind of like an analog to WebGL, or are you really just handing over all the control over to WebGL to do all of that?
So I mean, maybe 3JS has some way to control that too, but I know, let me see if I can go back a little bit. I mentioned that, oh wait, no, it's forward. The time here, nope. One more. So if you look at this render function, there's the timestamp itself. So there's actually like a quick little like formula that I didn't put here, but you could limit frame rate. I know it was the first question I got asked too, which was detecting people's hardware. I don't know the answer to that, but I'm sure if we found the answer to that, we might be able to you detect their hardware and then limit the frame rate accordingly. But I know in games too, anytime you're rendering a scene and you're making like a transformation on an object, you always want to multiply by something called delta time, which is just this timestamp. And so that way, no matter how much time's elapsed between the frames, which is limited by the hardware itself, you're still going to get a consistent motion. It's just if you have really bad hardware, you might even like that timestamp might be super long, or it might crash your app or something because you run out of memory on your GPU or something like that.
Okay, so the delta time is how I would determine how far along in my animation I should be, right? And so it'll make it choppy, but it'll essentially always synchronize with the correct time, even if it's not fluid. That's what delta time gives us.
Yes. Yeah, you explained that better than me.
That makes sense.
Dan?
Just kind of jumping in because I ran into this like frame rate dips because of this, right? It calls it every animation frame, but if your animation frame takes too long, the entire DOM render will pause. So like your CSS animations and everything will get choppy. We actually ran into this because if you disable hardware acceleration, your GPU is not used at all by the browser. All of that goes to the CPU. Whole thing runs like crap. And you'll have like, your like the entire that tab will just freeze up and everything goes really slow. And we couldn't find any way to detect it. But another thing that I want to throw out there with 3JS, because you had mentioned how helpful it is, and it is, that delta time and everything, they have helper classes that just do that all for you.
That's what I suspected. That's awesome.
Oh, sorry.
Another question. I don't know.
Cool. Any more questions?
So what are you building with WebGL next?
So it's kind of a part of I kind of like, since I made a little graphics engine, I ported part of it over to this demo project that I shared just to save some time, but it's basically a little graphics engine. It just doesn't have so it's kind of like 3JS. It's getting towards something like that where you have things like materials that you can customize. Basically abstracts the WebGL, so it's a lot easier to use, which I think is what, if any of you are using it, you should try to do. But I think it'd be cool to have like a little mini game engine within a browser. Just I would have to start doing some more stuff like ray casting, more physics things like bounding boxes around objects, so you can detect. Because without bounding boxes, you have no way of actually knowing when a model is even like inside another model, and that's a whole nother thing you have to calculate. And a lot of that, I think, you have to do on the CPU actually. But yeah, so answer your question. I think like a web game engine could be kind of cool, like a very basic one.